Thank you. I'd like to provide an overview of some of the work some of my students and I have been doing for the past few years. Most of what I'll talk about has been published, but the work, of course, is continuing with the new generation of students. For about the past 7 or 8 years, we've been working in a variety of the shale gas, which are the red, tight oil, which are the green, and sort of the combined oil and gas producing areas, mostly in North America, a little bit abroad. And there's a lot of diversity in these different basins, and the challenges are different from place to place. Today I want to talk about 4 items: the enigma of unconventional resource production. Let's explain what I mean, the importance of viscoplasticity of the shales and its effect on stress magnitudes, the occurrence of both seismic and aseismic deformation accompanying multi-stage hydraulic fracturing, and some issues about how matrix permeability couples back to other properties. And I've indicated, Sone was the lead researcher on this project, Kohli on this one, and Rob Heller on the last. Now, if you're not familiar with how this works, horizontal wells are drilled, they're perforated multiple times over a few hundred feet. It's all stimulated at once. Hydraulic fractures propagate from each set of perfs, and multiple small shear events, microseismic events, occur in a cloud around these. And then you do it multiple times, working from the toe to the heel, and then you drill and parallel wells, and presumably you're going to produce from this entire stimulated rock volume as it's known. And basically what you're doing is you're creating a lot of surface area in contact with the very low matrix permeability. Now, the problem in understanding production is that when you actually count the number of microearthquakes and consider how they affect the reservoir, it's kind of hard to account for all the gas that's produced, say, in a dry gas reservoir. What I mean by that is a magnitude -2 event is a patch about 1 meter in size, and it slips about 1/10 of a millimeter. So if you take about 100 of those events per stage, which is fairly typical, and you distribute them through the volume of say, one hydrofrac stage, where the hydrofrac is about 100 meters high, the interval here is about 100 meters or so, and it's going 100 or 200 meters. Imagine the well going through the middle there in either direction. 100-meter size little slip events doesn't touch very much of the reservoir. It's hard to see how they even touch each other and provide an interconnected flow path to the hydrofrac and back to the well. So that's one problem, and in fact, the other challenge is not only are we producing more than the deformation would obviously explain, we're producing far less than we'd like to be producing. And after 150,000 horizontal multi-stage fracked wells, the average recovery factors from dry gas wells is only about 25%. And the tight oil you're familiar with in the Bakken and the Eagle Ford and the natural gas liquids in the Marcellus, the estimates are that you're only getting between 2 and 10%, maybe an average of 5% or so. So the recovery factors are both higher and lower than logic would dictate. And so the question is, why is the stimulation so non-uniform? Now, in these 5 wells, each well was fracked about 10 times in almost exactly the same way. There was a seismic array in the middle well that moved along the length of the well. So when we see very few microseismic events here, it's not because we're further from the seismic array and we're just not detecting the events. Those events, in fact, did not occur. So let's talk about seismic and aseismic shearing during hydraulic fracturing. And we've been talking about this for a few years, and we've put a couple of papers in sort of petroleum meetings related to it. And you can basically understand why we're arguing that there's a lot of slowly slipping faults. There's more shear deformation occurring than we're aware of, because when these shear events occur, they are in fact not propagating at something close to the shear velocity. They are not emanating seismic waves, and they're in fact slow slip. And Kohli led a big lab suite of experiments using rate and state friction to try to distinguish how the composition of the rock affected whether or not the rocks were velocity strengthening and therefore expected to slip slowly, or velocity weakening and therefore expected to slip unstably and produce a microseismic event. And basically, in the first study we did, we concentrated on variations of clay content. And as your intuition might indicate, the higher the clay content, the more likely it is that the events slip stably. Now, in these shale basins, they have markedly different compositions. And so maybe the subtext of my talk should be that the rocks matter. And some of the shales that we deal with are, in fact, limestone. And some of the formations do have, on the order of 50 or more percent clay, and that matters a lot. These are two samples out of the Barnett shale, so same formation, but what we call Barnett dark or high clay and Barnett light or low clay. So even within a given formation, there's a lot of variability. Now, this is from the paper that Arjun and I published in JGR, and it shows the decrease in the friction coefficient from about 0.8 to about 0.45 as a function of the sum of clay content plus organic content. In other words, how much soft stuff there is. There's only a few percent of kerogen in there, so this is mostly clay, and so the friction decreases slowly. But looking at A minus B, of course, when A minus B is negative, we get stick slip behavior. When A minus B is positive, we get stable sliding. There's a very abrupt transition at just above 30% clay, and all of these samples are stick slipping and would expect to represent the kinds of formations in which you'd get microearthquakes, detect microearthquakes, and all of these samples have enough clay that they're stable sliding. And the amazing thing is that when you see the same name on sort of low clay and high clay end members, these are samples that come out of the same core barrel. So samples of a formation only a few meters apart have enough variation in composition that you get markedly different behavior. But it's perfectly logical that the higher clay end members are simply not going to produce microearthquakes, despite the fact that the shearing is going on, despite the fact that the shearing is contributing to permeability. Another reason you get stable sliding can be shown through some modeling here that Mark McClure led, but basically it's like this. When you're pumping at the magnitude of the least principal stress, which you do when you're propagating hydraulic fractures, you can make very poorly oriented faults slip. Okay, pore pressure is very high, effective normal stress can become very low simply because you're pumping at such high pressure. When a poorly oriented fault slips, it can't propagate, say, at the shear velocity, which is what we need for seismic rupture. It can only propagate as fast as the fluid pressure can move along that fault. And therefore, even though the fault slips, even though that shearing might assist in production, it's not going to generate a seismic event. And it's the initiation of slip on poorly oriented faults that makes this whole process work. Most of the faults we're dealing with in these shale formations are old, dead faults and are not active by any kind of reasonable geologic measure. Now, Indrajit Das and I published a couple of papers in geophysics showing what we think is evidence of slow slip on larger faults. These we call long period, long duration seismic events. They look just like tectonic tremor that's seen on the deep San Andreas fault and in various subduction zones. And by analogy, we believe that's what's happening. But it takes a big fault to produce a seismic event with a duration of tens of seconds. And so they're not seen everywhere, but we've seen them in a number of places. In the case of these same 5 wells, when the array was about here, we could get the general area they were coming from. You can't see clear P and S wave arrivals, but you could see the move out coming across the array. And in subsequent work that Noah Fargal has done, we've actually identified the fault through 3D seismic data, which was done well after the fact. That seems to be the fault that's poorly oriented, but at the pressures involved, capable of slipping. And it even explains a cluster of faults seen in an FMI log, which appear to be the damage zone adjacent to that larger fault. So we think there's a lot of aseismic deformation occurring in these reservoirs during the multi-stage hydraulic fracturing. Now, the work that Hiroki led is mostly looking at the viscoplasticity of these shales. Now, we've been looking at this in my research group for a number of years, but in materials that are not surprisingly viscoplastic, very weak sands, or the gumbo shales of the Gulf of Mexico where there's been very little diagenesis. These are real rocks. They have a Young's modulus of 50 gigapascals. They have a rock strength of 1 to 200 megapascals. These are real rocks, and yet we see appreciable time-dependent deformation under a constant load when the clay content increases. And so this is the Haynesville sample up here, but they really do creep. Now, the interesting thing about creep is that, under this kind of loading condition, it creeps as a function of time. Under this kind of loading condition, where we hold the strain constant, the stresses relax as a function of time. So we've developed a constitutive law. Since it's all published, I'm going to kind of run through it and just give you the general points. We developed a constitutive law. The constitutive law has two parameters. One, this parameter B is just 1 over Young's modulus. This exponent n right now has to be determined experimentally. And as a reality check, we calculate the creep strain over very long periods of time, and we find that even the creepiest rocks up here are only deforming a given rock sample by a couple % over geologic time, so it's fairly reasonable. Even though the rock creeps forever, the creep rate decreases so fast with time that the amount of creep is really finite, and you can talk about it even though you're talking about a rock that, in theory at least, is creeping forever. We can then turn that into stress magnitudes and see that the stress magnitudes we get for the rocks with very low clay, the rocks that are hardly creeping, are a few thousand psi, which is the kinds of stress differences that we observe, and much, much lower stress differences. The stresses become much more isotropic in the clay-rich samples. Now, if you're in a normal faulting domain and the stresses become more isotropic, this means the minimum stress approaches the vertical stress, right? And if you're doing hydraulic fracturing, the minimum stress is the frac gradient, right? So it means it's harder to hydraulically fracture the clay-rich rocks. And this kind of explains what's been known forever in the oil and gas industry, and that is that shales are often good frac barriers. The stresses are relaxed, the frac gradient is higher in the shales than in the sand, so you frac the sand and the frac does not run up or down. Now, that's not always the case. We're doing so much of this in so many different rocks, and we can see this is work from Pinnacle. Here's the depth of the Barnett Shale. The spiky signal is the shallowest and the deepest microearthquakes. The produced water is way up here, and what you can see in some areas in the Barnett, the real problem is the downward propagation of the hydrofracts into the Ellenberger. And in a recent paper by Hiroki and I, we take our model, we take the lab measurements, and we try to predict why we see this downward propagation in terms of the contrast in viscoplastic properties. Okay, the third and final topic I want to address is permeability. And these rocks all have in common extremely low permeabilities. That's why we're doing the multi-stage hydraulic fracturing. Now, here's it's somewhat dated data, but it's absolutely characteristic of all the data that's come since then. It's from Peter Valco and John Lee, two petroleum engineering professors, I think now retired from Texas A&M. They were looking at the Barnett Shale. They took monthly averages of all the wells drilled in July 2004, 2005, and 2006, and show the monthly average production as a function of time. So here, the wells are getting better very fast. The laterals are getting longer. They're doing more frac stages per lateral, okay? But what you can see is that the production rates decline very rapidly. So that's an issue of real concern. We'd like the wells to last longer. Why does the production decline so fast? Well, one reason the production declines so fast is that the permeability is sensitive to effective stress. And so Here we show 3 samples, 1 Marcellus, 2 different Eagle Ford samples, and as a function of effective stress, the permeability is dropping by about a factor of 2 or 3 as you go from effective stresses relevant to the undepleted case to, a fairly well-depleted reservoir. So that's clearly something to take into account. I do want to make the point here that these are sort of nano-Darcy scale permeabilities. I hope you can read that. And these are micro-Darcy scale permeabilities, much, much higher permeabilities. And so this kind of natural variation is extremely important. And I'll get to the reason for that in just a minute. Now, if it's the surface area associated with not only the hydrofracks themselves, but all the shearing that goes on, that's contributing to the permeability, one question we have to ask ourselves is whether this, the permeability induced by shearing on these faults is actually decreasing with time, almost like the faults are sort of healing, and so that the fracture network is less capable of delivering gas, from the matrix through the shear fractures back to the hydrofrac and into the well. Now, the reason this is so important is that if you think about all these different fractures as being places where there's one-dimensional flow, it flows out of the matrix into the area of a given fracture. Maybe it's one of these little shear fractures, maybe it's the hydrofrac, but if you add them all up, they have an area. And when you look at linear flow, it turns out that whether we're talking about the cumulative flow or the flow rate, this parameter alpha, which is the area times the square root of matrix permeability, is what's controlling the production. And so, the flow rate, your ability to produce from these reservoirs, really depends on the creation of this area, based on what the matrix permeability is, which is something we can't control. So when the matrix permeability is in the tens of nanodarcy range, we have to create enough area to compensate for that extremely low permeability, and we do that through this distributed fracture network. And water is used, slick water is used for the hydrofrac fluid so that it has a low viscosity so it can penetrate pre-existing faults and create this fracture network. When the permeability is in the microdarcy range, you don't really need the fracture network so much. You can actually create the area you need with a large hydraulic fracture. And so one thing we have to think about is whether or not these things, which are very key in contributing greatly in the initial production, becomes less productive at time, and that sets the groundwork for things like refracking these wells, which a number of people have started doing or thinking about. There's not a whole lot going on simply because of the low oil and gas prices. Now, there's another enigma about production. Not only does it fall off fast, it doesn't decay fast enough. So if you look at this part of the curve, the curves are actually too fast. You would expect, in fact, as permeability is going down, as maybe these fractures are healing, that the production would tail off. And this paper that Valco and Lee wrote was really not about explaining this, but was explaining this flattening of the curves. So we've been looking at that because we're talking about nanometers, tens of nanometer scale pores. One would expect, based on the mean free path of these gases, that as we change from an original pressure to depleted pressure, we actually go from the Darcy flow into slip flow, sort of a Knudsen diffusion effect. And in fact, when we back calculate these measurements after making measurements of permeability at very low pore pressures, we can actually cause this Knudsen diffusion to occur. In the literature, it's sometimes called the Klinkenberg effect. We can cause it to occur. And what we see is that in some of these samples, as the pressure goes down, the permeability, the apparent permeability is not really changing, but the apparent permeability increases markedly. So 150,000 wells later, we're not doing a very good job of recovering the hydrocarbons, and there's a lot to be learned and a lot more to do. Thank you very much.
Thank you, Mark.